This is the Aircraft Design Project by Group 104 for Fluid Mechanics. The agenda for this presentation is to first introduce the goals of this project, followed by the design steps and calculations, 2 additional wow factor discussion points, and finally the conclusion. The goal of this project was to design aspects of an aircraft using the tools acquired over the semester. This was achieved through research and engineering assumptions, as well as fluid dynamic theories.
For our design, we were interested in researching a larger commercial aircraft. Keeping that in mind, we chose to model our design off of a Boeing 747-8. Using the Boeing 747-8 as a reference, we were able to research the liftoff and cruising velocities as well as the cruising altitude. The next thing we looked at was the volume of the fuselage, and we found that the diameter of the fuselage to be around 6.1 meters. Then finally, we researched the weight of the aircraft, accounting for the weight of the fuselage, the average weight of a person, and the number of passengers a Boeing 747 can carry, the average weight of luggage per person, and the wing weight. The total weight of the aircraft for the design was determined to be 525,274 kilograms.
When selecting an airfoil, we went out and we looked at similar aircrafts and their airfoils to see what the positives were about them. Some of the things we noticed is that they typically have a rounded front, which decreases sensitivity to the angle of attack, which aids in control and having just a smoother flight in general. We also notice that they have a positive camber. This helps in increasing lift at higher angles of attack. And we noticed that they were relatively thin. So we decided to kind of go with something similar with our airfoil. We still kept that positive camber. We went slightly lower though, due to the fact that we're at higher velocities than these other two aircrafts, and we were slightly thicker. This will add a little bit more structural support to our wing and aid in fuel storage. When it came to wing design, we first had to figure out how much weight we were actually lifting. So we used the mass of the aircraft times gravity to give us the amount we had to lift, and then we were able to use that in the lift equation along with our coefficient of lift we got from the coefficient of lift versus angle of attack, and we optimized that to be about at an angle of attack about 12.5%, well 12.5 degrees, which gave us a coefficient of lift of 1.4. This gave us our area, which we selected an aspect ratio of 4, which leads to a span of 63.16 meters and a chord of 15.58. So this falls right in line with typical commercial airliners, which means that in commercial airports we're going to be having no issues as far as maneuverability, which that's one of the bigger issues with span. But being that ours is a little bit shorter than some of them, we're going to have improved strength and maneuverability in the air compared to them. When it came to calculating our drag, we just went with basically the same way you calculate the lift. We optimized the drag coefficient to be lowest at, we will find out what angle of attack it was lowest, which is about 2 degrees. But anywhere between about 0 and 5 degrees was pretty much the same. So then we've just put that into our drag equation here, give us a combined drag of 193.46 kilonewtons, but this does not account for induced drag, which typically is 10 to 20%. But being that the lift-induced drag equation is a function of the aspect ratio, and with lower aspect ratios it comes a higher induced drag, I'm expecting that we're going to be significantly higher than this, since we have an aspect ratio of 4 when typical aspect ratios are from 6 to 10.
The power required to maintain cruising conditions, which was found by multiplying the cruising velocity by the drag force, was found to be 56.16 megawatts. Because this aircraft is so large, a large amount of power is needed as well, requiring the use of jet engines. Our design is modeled off the GE90-115B, where each engine can produce 23 megawatts of power. In order to power our designed aircraft, a minimum of 3 jet engines would be required. To improve balance of the overall aircraft and to prepare in case of an engine failure, a 4th engine would be added. This would also increase the life of the engine because they could operate at lower power when additional engines are added.
Following the tutorial for ANSYS Fluent, CFD of the airfoil was conducted. This process included creating a mesh using sphere of influence, division, and inflation parameters. Boundary conditions were set, and then the calculation was run. As you can see in the results, 3 iterations were run with decreases in element size for each simulation. These iterations produced values within 10% of each other, but these values were 20% off from the values we pulled from the airfoil graph. This indicated just how much there is to learn about CFD and mesh refinement.
The historical analysis for this project focused on the emergence of large-scale commercial aircraft when the Boeing 747 was introduced. Initially a proposed design for large military transport, Boeing used it as an alternative plan for the commercial industry when it lost the bid for the military. This plane was the first of its kind, and as a result had historic challenges and historic benefits to the airline industry. The major challenges were finding an engine that could provide enough power to the plane, the sheer size of the aircraft and its wingspan, and the huge financial investment it takes when making a plane this size. However, there were benefits that were found, and the Boeing 747 was a highly successful competitor. It allowed for airlines to reduce seat cost, carry passengers for longer distances, and a profitable market when it came to transporting large products.
While this design was modeled after a Boeing 747-8 aircraft, there are some differences between our design and reality. In our assumptions, the fuselage was assumed to be perfectly streamlined body. Our design equations assumed a constant chord length for an infinite length wing. Also, the Reynolds number at takeoff exceeded the data available for the lift coefficient, so the data was extrapolated using the trends of the lower Reynolds numbers. These slight errors could result in minor differences from what our calculations predict to reality. In further analysis, a factor of safety could be applied to ensure that the aircraft performs as expected, and an economic analysis could be done to optimize the engine power and the cost of materials.